Oh, am I on? I think I am on. Well, it's dark in here though. All right, I'll be back.
Sounds good.
I gotta do a couple things.
Yeah, that's fine.
All right, hello everybody. Sorry for a little late start here. Just getting your exam ready to go. I had it all ready, but I'm like, oh wait, I have to make a Dropbox. I gotta have the news post ready to come up. That way it should pop up automatically after class today. So I think everything should be ready to go. Okay, so today we're going to focus on questions, homework questions, or I'm going to open up the chapter 16, chapter 17 examples. There's like a bunch of problems. Usually we would spend the class just kind of working on them together and then maybe talking about them. So that's kind of what we'll do today as well. And then right after class, the exam will pop up. If you want to wait to get started, you can start later if you want. But I'm really expecting that everyone will do their studying first, then open the exam, right? So you can start tomorrow at 10 if you want, and you can continue studying. I don't care. The deadline is tomorrow at midnight, but I don't want you to open the exam and then say, oh, I need to study that more, and then go back. So I'm kind of trusting that you're doing that. This is why, like, if we move online in the fall, where they're still trying to figure out what they're going to do. Let's say we were to do that, you probably would have a 2-hour window to take your test, and that's all. You'd have we wouldn't have class today. It would open at 2. You'd have to turn it in by 4, maybe even 3:30 or something. You'd have a limited window, so you can't open it up and then go study that stuff and then come back. So just assume you can use as much time as you need to study, and then when you're ready, you pop it up, you open it up, and then you're working on the exam after that. If you need to take a break and finish, that's fine, but no more studying after that point. And that'll be due to the Dropbox by midnight tomorrow. So you got lots of time to work on that. Yeah, I think that's all the announcements I had. So I think what I will do next is I can pop up the chat window. And I don't have the homework up yet, but I can get that up. So let's maybe start there. I know you've been working on continuing in chapter 17, but let's start. I don't know if there are any questions. Let's focus today's homework questions on ones that are relevant for the exam. So anything up to 17.3, just through 17.3. So no Green's theorem, no divergence of curl. 17.5, 17.4. So any questions up through in the homework up through 17.3? 17.3, number 42. We have a request for that one. All right, let's get that one up. Uh-oh. Well, that's kind of cool. You can see the green screen. I bumped my camera. Oh no. Oh, technical issues. Now it's all jacked up. Oh boy. Kind of. All right, 17.3. I have it on this tiny little tripod behind my monitor. It's a webcam. Normally you just clip them onto the monitor, but the monitor is really wobbly. And so whenever I'm writing on the desk, the monitor kind of shakes. And so then the camera shakes too. It just does, it's not good. Okay, 42. What are we doing here? We are using the fundamental theorem for line integrals. Verify that the fundamental theorem of calculus can be used, and then evaluate the line integral. Okay, there's an easy way and a hard way to do this problem.
Really quick, can I see, since it goes from 0 to 4 pi, do you just plug in those values into the vector function and then you use those as the points?
Yes.
For say theta b? Okay, because that's what I did. So I was just wondering if that's correct.
That is correct. Yeah, I was going to say that there's an easy and a hard way to do this one. Apparently, there's an easy and a hard way to paste this into. So the hard way would be to ignore the instructions and not use the fundamental theorem of calculus and say, well, okay, I need to take a gradient. So let me take the gradient and then dot product with dr. And then here's my, so I'll do my r prime of t dt. So you'd have the integral, the line integral of the gradient. So derivative with respect to x would be 2xyz. Derivative with respect to y, x squared z. Derivative with respect to z, x squared y. And then dot product with r prime negative 2 sine 2t, 2 cosine 2t, 1 dt. Integrate that from 0 to 4 pi. And no, we haven't even plugged in the x, y, and z yet. Okay, so that is a really bad idea. We should use the fundamental theorem of calculus here. And so I'll get to Michael's question here, because the fundamental theorem of calculus says, oh, you can, if your field is conservative, you can just evaluate phi at the end point minus phi at the beginning point, but we don't have a beginning and ending point per se. But what you nailed it, because we know t is from 0 to 4 pi, the initial point would be, it's in its vector form, but it would be cosine of 0, sine of 0, 0. And then b would be cosine of 4 pi. Oh, it's not. I was going to say it's back where it started. No, not quite back where it started. It's not a closed curve. I was thinking because 4 pi and cosine and sine are going to be the same there, but the z value is different. So this one is a spiral, or a helix, I should say. It's a helix because the z is not the same. So yes, exactly what you would do. Do you know what the phi is, Michael? Did you have that part squared away?
Yeah, isn't it just 1 plus x squared yz?
Right, because the definition of conservative means that the field is the gradient of some phi. Well, I mean, our field is the gradient of 1 plus x squared yz. That implies that our phi is 1 plus x squared yz. You nailed it. Yep. And so we would just evaluate those at each of these endpoints, 1, 0, 0, and 1, 0, 4 pi.
All right, cool. Thanks.
Mm-hmm.
I got 0, so if anybody else got that.
Right, because the y coordinate is 0, so the x squared yz part of it is going to be 0, and then you just have 1 minus 1. So that makes, I think that sounds right.
Got it.
And I think, did I post those answers? I feel like I did.
Oh, I think I forgot. I forgot to check them. I forgot that you did that.
No, it's
so.
okay. Yeah. So just for future reference, they're up there. And so, yeah, they are posted. So we should be able to see that. But this is a good question. It's a good question. Yep. Lots of good stuff in there. So, nope. There it is. Yep. Looks good. That's what we were just saying. All right, good. Any other specific homework questions?
Luxembourg, and this was about 8 years ago.
Any additional homework questions? Through anything through 17.3. Okay, feel free to pop in later. I got the chat up, so feel free to jump in at any point. Let's do a quick question. I always like to ask this about what will be on the exam. So to clarify, we have 16, 1, 2, 3, 4, 5, 17, 1, 2, 3. Okay, so those are the sections. What is, I'm trying to remember all the integrals in chapter 16. It starts with double integrals over rectangles. Okay. So double integral over rectangular region, double integral over a general region, double integral over polar, triple integrals, and then triple integrals over cylindrical and spherical. And then we have vector fields, line integrals, There's different versions of those. And then we have conservative fields. There are a bunch of theorems associated with it. So that's the content. I have the test ready to go. There are less questions worth more points. So there's one question that has some subparts, but otherwise the other questions like all worth 12 points each. Do not infer that they all are the same amount of labor. I didn't want to give any hints away. So like, oh, this one's harder, so it's worth more points. So they're all the same amount of points. And so there should be one or two. You're like, this is deceptively easy. So, you know, double check yourself. Like maybe you are looking at it the wrong way, but that should occur on at least one, maybe two of the questions where like, oh, okay, as long as you know what you're doing, it should be an easier one. And then some of them seem like, man, I did the work of like 20 points here, but that's the trade-off of not giving them away. So they're all the same. The one that's got some subparts to it, the parts are all equally weighted. I think there's 3 parts and 6 points each. So I think there's a total of 9 questions, 10 questions, if you added up the individual parts. So there's a lot of stuff that's going to be left off. You know, we could do 10 questions just from chapter 17. And so you're not going to have every single type in there. I want to try to address at least one from the main, you know, double integrals, polar coordinates. Cylindrical kind of covers polar coordinates, so you could kind of do one or the other. Spherical coordinates, vector fields. Fields can kind of get covered in conservative fields. There's some overlap there too. So we'll try to hit all the main sections. So do you have any questions on what you should know, what will be on the test, anything like that? Okay. Let me open up the review problems. These are in D2L. If you recall, these are just a list of lots and lots of examples. Let's talk about which ones we don't need to bother with because we didn't cover them. So let's take a look here. Chapter 16 review. What we're looking for is like centers of mass. That's 16.6. Probably near the end. There are many. Oh, to find the center of mass, find the center of mass, center of mass. So it's the last 3. The last 3 from chapter 16, those are 3 we can leave off. So don't worry about 25, 26, 27. I do think finding the mass itself is not crazy because we've done a problem like that, I think, in the notes about just, you know, you have this density. So you just integrate the density to find the mass. That's not a center. The center of mass is more complex. So we won't have to do those. And then let's look at chapter 17. I'm a little more worried about these because let me actually pull them up. We can make some notes on them. They're not necessarily in order is the problem. If I were more prepared, I would have had just exactly the ones that were on the test. But one of the things, by the way, I'm going to send out probably tomorrow to all of my students. We've talked about we're not sure what's going to happen next fall. And so one of the things I want to know is like, well, okay, so if we go online next fall, was there stuff that we're doing now that's good? Like we should keep doing it? Was there stuff we're doing now that's not good? Or like stop doing that? That's not helpful. And then is there stuff we're not doing now that we should be doing? So kind of 3 open-ended questions. What do you like about how the class ran for the last 8 weeks? What did you not like? And like, don't do that again. Like that was not good. And then Like, what should we have done? Is there other stuff we could have added? And so just kind of, I just want to be a little more prepared, because I kind of just, spur of the moment, hey, we're going online. Okay, well, here's what I think I'm going to do. So let's talk about a chapter 7 review, what we could have. So fields, okay, vector fields, constant vector. So those are okay. Match the vector fields, okay, that's fine. Find the vector field, find the gradient field, that's fine. Okay, that's fine, 5 is fine. Line integrals, okay, those are all fine. 10, work done, yep. Find the work required, work. Circulation and outward flux, yep, that's fine. The flow of water, find the flux across the cross section, all right. Determine whether if they're conservative, yep, we talked about those. If they are, find a potential function. Evaluate the line integral, all fine. This is a more theoretical question. Prove that the radial field, blah, 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 is conservative. Find the value of P where it's conservative. That's a little more abstract one. Okay, then I think we're on to Green's theorem. So I think we can draw a line at 26. Find the area, that's Green's theorem. Circulation on the boundary. Yeah, that's Green's theorem, and then it becomes, divergence and curl, that's 7.5. Surface integral is 17.6, so, yep. So it looks like anything through 26. So in the practice, if you have questions right now, the ones we want to focus on are, where did the 16.6 go? Or chapter 16. I don't know where it went. Anything up through, what did we say? The last 3 in chapter 16, and then anything up through 26 in the chapter 17. So I don't know if you've started chipping away at these, or if there are any that catch your eye right now that you're looking at. I'm happy to give you a few minutes to kind of look through. Why don't we do that? I know some people are just looking now, so why don't we take, I don't know, like 3 minutes or something. I'm going to step away for a second. I got to check on the kids anyway. So I'm going to check away, and then why don't you type in the chat some questions you want to look at from either the chapter 16 review up through the last 3, or the chapter 17 review up through number 26. Right? Just take a couple minutes and put some requests in the chat, and we'll try to grind out as many as we can. And I'll be right back. All right. So what are we thinking? Anybody have any in particular that you wanted us to work out? The chat is quiet today. It's like silent today. I don't know if this is overconfidence or exhaustion. Michael, what were you going to say?
Can we do, wait, isn't curl and stuff in like 17.4? Or is that
That's a good
divergence?
question. Because I'm trying to think. I know we introduced it's circulation and flux that got introduced in 17.2, circulation and flux. So you're right. I think that first question there, that letter A, right? So, or, yeah, even seems like A, B, C, and D are all a little more advanced. They're like simple questions, but I think they're from later sections, aren't they? Because you're right, curl and divergence. This is that gradient operator, which is from 17.5. Curl, divergence. I don't even know how to do E. I haven't looked at it. So I'd have to think about that one to figure exactly how to do that one. So yeah, I think you're right. So those, we can hold on to these for the final. Philip asked about 17.2, number 25, just how to set up the integral. So let's take a look at that one. It's crazy when you have like a decent sized house and there's so much banging that I'm vibrating. I don't think the picture is accurately representing that, but every once in a while, like the whole house shakes. Then you just wait. Nope, no crying. Okay, they're good. 25. Oh yeah, okay. I feel like we talked about this one, but these are good. Just maybe it was a different one that we did. These are always good. Just practice setting them up. And these we're going to do, they're a line integral, right? Evaluate the line integral. So we might have multiple methods to do it, but at this point, we're going to work on doing it as a line integral. All right, am I looking at the right one, Philip? Just want to make sure. Okay, cool. All right, so I like a picture. So let me draw a picture of the curve. Circle radius 4, centered at the origin. Okay, picture of the path, I should say. That's C and 4. Okay, so in general, the line integral of a function ds, you're going to want to have this written down, is f of xy times the magnitude of r prime of t dt. There's always some confusion here because we, like toward the end of the chapter, then in 17.3, and then also continuing on in 4, we do these fields and the dot product with r prime of t. And so some people get confused and they have this function and they try to do a dot product with r prime, but you can't do a dot product of a function with a vector. So here you have to have a function of t when you're done. Okay, so we're going to do a line integral over the curve. The function will become, oh, I don't have a path yet. Okay, oops. All right, so I need to get this path. There's no one way to do the path. It doesn't give you a direction or anything. It just says it's the circle of radius 4 centered at the origin. So you can do the path however you want. I would probably just do the unit circle and scaled. That's what I would probably do. So I would probably take the unit circle is r of t equals cosine of t sine of t. So then I would just scale it for hours, just scale it by 4. And so now we have the circle radius 4 centered at the origin. Now we do want to get the entire circle. So what else do I need that I haven't specified yet? Max is right, we need the bounds. And so if we're gonna go all the way around, we would do t going from 0 to 2 pi. And you'd catch it when you got to the integral. You're like, oh, I forgot my bounds for my integral. So no sweat if you forget, you'll catch it later. Okay, so now we have the function. Now we have to plug in what x and y are equal to. So when we plug them in, x squared will be 16 cosine squared t. And then y squared will be 16 sine squared t. Okay, then I need to find the magnitude of r prime. So let me go down below here. R prime, -4 sine t, 4 cosine t. By the way, if you're doing this right now and you can kind of see where things are leading, you're in a good spot for this test. That means you've done a lot of practice. So hopefully you can already see where this is leading. If not, it's okay. But I just wanted to, like, if you're thinking like, wait, can't you just, or isn't that just? Yes. So square root of -4 sine t squared plus 4 cosine t squared. We're gonna get 16 sine squared t plus 16 cosine squared t. And we can just factor 16 out. I don't even know if I need to write all this out. You can probably tell where we're going. Sine squared plus cosine squared is 1, so we just get 4. Very convenient. That was our magnitude. That was our magnitude of r prime. And so you can actually do the same thing in the integrand here. You can factor out a 16, you get cosine squared plus sine squared, which is 1. So we actually just get the integral of 64 dt. Nice. 64 theta. I know you just asked to set up the integral, Philip, but I thought I'd just keep going. 0 to 2 pi. 64 times 2 pi will be 128 pi. The reason why that one was like, wait a minute, where'd all the t's go? Well, just think about it. Look at the function. This is a z value. And z is square the x plus square the y. Okay, but you're always on a circle. Well, on a circle centered at the origin, x squared plus y squared is constant. That's the equation for a circle centered at the origin is x squared plus y squared equals r squared. That's the formula for the equation of a circle. So x squared plus y squared is just 16. It will always be 16. So it's not that x squared plus y squared, this function, it's not that this function is constant. What's true is along that circle, it's always 16 height. It's always a constant 16 height along that circle. And so that's why we just got 16 for that function. And then r prime of t is just constant as well, because it's moving at a constant rate around the circle. So everything's just constant. It's a constant height and a constant rate. So that's why there was no t in that function. Yeah, Philip here, the key is when you're doing line integrals. Line integrals are integrals dt, so it means you need to have t values there. So the polar coordinates are going to be irrelevant here for a line integral. Polar coordinates are only relevant in double integrals. So yeah, so it feels like it should apply because you're like, it's a circle, polar coordinates. But line integrals are always single variable integrals here. And so you're going to want to leave it there. We'll actually learn in 17.4 when we can convert a line integral to a double integral. So for example, I don't know if are there any like here. So here's an example from 17.4, not on this test, but here's an example from 17.4 where you're going along the path, but the whole point of Green's theorem is you could convert it to an integral over the area. And that area, you do that area as in polar coordinates. It's much easier to do the area in polar coordinates. So once you get Green's theorem, it might be applicable, but Green's theorem doesn't always apply. Green's theorem only gets used when it's a closed integral. And certainly Green's theorem is not going to be relevant for this test anyway. so I like the recognition of a circle, but for line integrals, that will not be applicable. So, that's a good one. Any other questions on that one, on number 25? All right. Other requests? Any other requests?
Think we could go over like matching the vector fields, just some of them.
Yeah. Yep. We haven't. I don't feel like we've talked a lot about that in class. In fact, I was. Oops, wrong thing here. Last night for the evening section, I started early and like, oh, let me pause the recording because it was like 10 minutes before class. I just got on, was saying hello and stuff, and then I forgot to hit like resume recording. I am recording this, but then I'm like, oh no, like all those examples, they didn't get to see them. So what I did is I went back and I gave them links to all of yours. And then I went in the descriptions. I don't know if anyone's been up, but if you want to see some of the ones we did last week, I actually went in the YouTube descriptions and linked to each example's, when each example starts. And I was looking at which problems we did. And I was noticing I only found one 17.1 homework question. But like we didn't do a lot of 17.1, so it's kind of good that you're asking it because we didn't really do any of those. So like if you look at, here's one, where's this stats? So like from Wednesday. And so I posted in the description like each question number. You can kind of skip to it. So I was noticing like, oh yeah, we did not do much from 17.1. So let's take a look there. Where did it go? Okay. Well, I will say that whenever you have a field that is just x, y, or some scaled version of that, that's a radial field and it's going into the origin. So there are only two options there. It's either B or D. Now, there's another radial field here, but it's a little hidden. Does anyone see what the other radial field is from the lowercase a through f? There's another radial field in there.
B.
Sorry, could you repeat it? I think when you unmute, sometimes there's like a little delay.
B.
B. It is not, because it switches the x and y. So I don't think that one will be radial. We can figure it out, but I don't think it will be. You might look at C and wonder what is this R? Well, if you look up above, R is that xy vector. So this is actually x, y over the magnitude of that, so square root of x squared plus y squared. What is the difference between A and C?
It's like C's like the unit form, I guess. Yeah.
So looking at the graphs, how are we going to tell which one is which? Oh, and Max is, are you typing, Max? You can just nod. Okay, Max is typing. Max has an answer for us. He's typing. He doesn't want to risk speaking. Last time we just couldn't get the audio to work. One is scaled. Okay, you're gonna have to type more or say more. You might have to risk unmuting yourself. What do you mean scaled?
All right, can you hear me?
Yep.
Perfect. Okay. So what I meant by that is that so one of them is going to be, so if you plug in an x and a y value, you're just going to get that xy value. But if you plug in the same values for the unit vector one, it's just going to equal 1. So it's going to be the same like layout for the radial vector field, except all the arrows are going to be at length of 1.
Yeah, exactly. So so that's what he's saying is that C, they're all going to be the same length. They're all going to be length 1. So which one must that be?
Be B then,
It has to
right?
be B. Has to be B. Yep. So B and D. Okay, we'll cross those off. We'll do process of elimination here. Cross those off. I don't know. Maybe just guess on some of the other ones. I don't know. Anybody have any ideas how to narrow down the list from the other ones?
I don't want to answer too many, but like I have an idea.
Well, maybe pick another one. Pick another one that you're pretty comfortable with.
F and C.
So, wait, no. I labeled them wrong, didn't I? It's not B and D. They're underneath them. That's mean. It's D and F.
And I mean F and E.
I know. Yeah, I know. Exactly. I knew it. That's why I'm like, wait a minute. That can be right. So the unit vector C here was D, and this one was F. So you mean lowercase f and graph C. Is that correct?
No, graph E.
Graph E. Oh, it looks like circles, kind of. Okay, so why do you think that?
Just because it's like trig. So like whenever I see trig, I'm like circles.
Some kind of circles. It's not crazy. That is totally reasonable. Well, let's think about this. Sine of pi x. So if x is 0, so we're on the y-axis. Okay, if x is 0, then all of those x components will be 0, and the y components will be sine of whatever pi times y is. So the issue is when I'm on the y-axis, all of the x components have to be 0. I don't know that they are. Right? So do you see what I'm saying? Like if x is equal to 0, meaning I'm on the y-axis, then sine of pi x would just be sine of 0, which is 0. So all the vectors would be, all the fields then would be, all the vectors would be 0 and then sine of pi times y.
Yeah, I get it.
And they don't look like they are. They look like they in fact get bigger and bigger and bigger when you get further away. Is there any that look like that? I feel like the first one looks like that. Oh, look at this. You see these like sinks, kind of like holes?
Yeah.
If you had to take a wild guess at where they occur, I'm not saying you as in Michael, but does anybody see? It looks like they're a little bit more than 3. That's weird. That's weird. Why would that? I feel like there's an error with this one because I was thinking like, oh, then sine of pi. I feel like that should be at 1, 1 though, not pi, pi. I think they screwed up here. I think that they meant this field to be sine of x, sine of y. That way it would be, there'd be no vector at every multiple of pi. I think they made a mistake on that one. I'm gonna open up Maple here. All right, so we're struggling with F. That is not an easy one. Let's see, B, negative 2y, 2x. So as x increases, the y component will increase because of the 2x. So as x increases, the y component increases. So that should get bigger as we go in the x direction. The y component should increase. Man, I don't see any that do that. And then as y gets bigger, the x component actually gets negative. What in the world? Okay, so we're gonna do a little cheating here with plots. Okay, and then we're gonna do field plot, and we have what was the one? Sine of pi. Oh, I think it's pi times x. Sine of pi times y. And I think if I remember correctly, it was x from like -4 to 4, y equals -4 to 4. Oh, missing a bracket. Yeah, that is not ours. So I think if I delete the pi in here, that's it. That's it. There's like these little holes at pi, because there's no vector there. It'd be sine of 0 or sine of pi. So it'd be 0, 0, no vector there, no vector at the origin, no vector at negative pi. So they screwed that one up. So this one we could actually say, okay, sine of x, that's A. Sine of x, sine of y, that's A. That's field A. Let's look at negative 2y, 2x. Let's check that one out. Negative 2 times y and 2 times x. Oh, interesting. So that's the one that ends up looking like a circle. Why is that? So I said, as x increases, the y component gets bigger. So as you go to the right, the y component gets bigger and bigger and bigger. Can everybody see that? Just track one thing as you go across. Do you see what's happening? As x gets larger and larger, the y component is getting larger and larger. And then when x gets larger in the negative direction, the y component gets larger, but also negative. Now now it's pointing down. So that fits. And then I'm going to erase this because that ended up not being true. The x component is negative 2y. So as y increases, the x component becomes more negative. Do you see the x component becoming more negative?
Yeah.
That's hard. That's hard.
It's confusing when like the y is in the x component.
It totally messes with you. I agree. Absolutely. These are not easy. So this one we said was E. Okay, so what do we have left? We did this one, we did this one. Okay, so E, you know what? I'm guessing that B has to be E. The reason why I'm saying that, do you see what's happening to the vectors as x and y increase? The vectors are getting smaller and smaller and smaller. And so what would make that happen? Well, if as x and y get bigger, it gets smaller. So that's why I think that one's going to be B. That definitely doesn't happen over here. Like here, x is this is the largest x, but the y component is getting bigger. That doesn't make any sense. The y component is getting bigger. That would not happen for this one. So this is, let's see, E is definitely B. So that means process of elimination, D must be C. The y component, this is again Michael's key complaint when they switch them on you. So the y component is equal to the x coordinate. So as x increases, kind of pick one and go across. As x increases, the y component increases. And you can kind of see them getting taller and taller and taller and taller and taller. As x increases, the y component increases. So those are hard. Definitely hard. All right. Christians, like, they're trying to set us up for failure here. Well, it's a good thing we asked about it, right? Because you would have never gotten that one right if we hadn't talked about it. So I think I need to go change the exam and put like 3 of these on there. All right. Other requests from, we got all of chapter 16, double integrals, triple integrals, lots of integrals, double integrals, triple integrals, line integrals. I see a typo. You see on number 9, verify that close, but there's no D. There should be a DS in there. Oops. It's a quiet afternoon. This was so much better when we were just like sitting in class and working. And you're kind of working with your table partner and I'm walking between. It's so much better. Daniel asked about chapter or number 17 on the chapter 16 review. All right, these are good. It's been a while since we've done these. I was looking at those when we were scrolling through. I'm like, oh, somebody should ask about those. It's been a while since we've done these. Okay. I wonder how this will feel, if this will feel easy now that we've done more of them, or if it'll be hard because it's been a while. I don't know. I think it's funny. I've told you a little bit about, my experience with Calc 3, how last fall was the first time I taught it, and I haven't had Calc 3 since 1994. So I was pretty nervous last fall, and then now this semester after doing it, now I'm not even like prepping for examples. I'm like, well, we'll just find some examples and I won't do them before class because we'll be fine. We can figure it out. And like, the more, just like anything, the more you do, the more comfortable you get. Okay, we want to find the volume. I don't know, Daniel, do you prefer to find like a double integral over a region of something dA? Or would you rather do a triple integral over a 3-dimensional region dV? Either will work here. Not always, but either will work here. Do you have a preference that you were thinking of, Daniel? If not, we could like do a vote too. We could just vote. All right, Daniel said either works for him. So let's do this. We're going to do a vote. We're going to use the yes, no. We're going to use the yes, no vote. Yes will be for double. And no will be for triple. Yes, no. Yes, no. So remember, you click on participants, and then you can see those options. Voting is ending in 5, 4. That's too many red votes. It's already no. Okay. All right. Voting has ended early. We're like New York. We're pulling Bernie off the ballot just because they think he's going to lose and they don't want him to win anyway. Okay. So my idea for triple integrals is think of a little representative piece in here. And here, because we have z equals, I would add them up vertically first. It's kind of a terrible drawing, but make a little pillar. So for my volume here, I would do dz first. And so z starts at the paraboloid. I need to make a little more space here. Starts at the paraboloid, 2x squared plus 1, and goes up to 3 minus 2y. And then I would look at the region in the xy plane, something like this. And I need to figure out what that region is. I don't know if that is obvious to you. We've done these before, but it's been 2 weeks. 2 weeks. So we're going to do either dy dx or dx dy. It kind of depends on what we decide here. So how do we find that intersection?
Set the z's equal to each other.
Yeah, that's correct. It's the intersection of the two curves. So that's that's 3 minus 2y equals 2x squared plus 1. And what you're really finding here is you're really finding a cylinder. You're finding the whole vertical cylinder where they intersect. And of course, that's the same. If it's a cylinder, that's also in the xy plane then. So that's why this works. So let me see here. I'm going to add 2y, subtract 2, subtract 2x squared. Oh, that's nice. And then divide by 2. Y equals 1 minus x squared. Huh. Did I go? That feels like too easy. No? It's fine. Subtract 1 gets you 2. So add 2y. Subtract 2x squared. Divide by 2. Okay. So 1, 1. And it turns out that this question mark is y equals 1 minus x squared. All right? Seems reasonable. So now I have to choose whether I want to do y first or x first. Anyone have a preference? Y integrating dy dx or dx dy? Okay, so Michael is asking about polar. You're thinking if it was a square root. Yeah, cylindrical or polar. Yeah, I know what you mean. But that would be if it was, this is not a circle. If it was square root of 1 minus x squared, that's a semicircle. This one is a parabola, so it's not a circle. So you do not want to do cylindrical here. Yeah, do not want to do it. So I would go with Max and Lisette, who both said dy first. And that's because I have y as a function of x. And so I could just do vertical. I could just go from 0 to 1 minus x squared. I would just go from 0 to 1 minus x squared, and then x goes from 0 to 1. I do like your idea, Michael, though, to keep your eye out for that, because there's no coordinate system provided here. So it doesn't tell you what coordinate system to use. So certainly being flexible is good. It just, the to get a semicircle, it has to be a square root, because a circle equation is x squared plus y squared equals r squared equals 1. And so you have to have a square root from the y equals. Any other questions on the setup here of the triple integral? Okay, let's do this then. I don't think this will be too hard. Should just be like a polynomial. This will be z from 2x squared plus 1 to 3 minus 2y dy dx. Now, I want to point something out in the next step. 0 to 1 minus x squared. This will be 3 minus 2y minus 2x squared plus 1 dy dx. Here's the question I have for you. What do I want to point out in this step? What point am I trying to make here?
This is the setup for the double integral.
That's correct. So everyone voted triple integral. Everyone voted triple integral. Well, except Daniel said he could do either one. But this is just the double integral. That's the double integral. So you could have just done a double integral, and you can kind of do the same thing. You have your representative piece, but you're kind of doing the vertically here. Well, the height of the piece is the top function minus the bottom function. So same thing. Okay, 0 to 1 integral. Oh, we can. We should probably simplify that. I want to integrate right now because I'm lazy, but we should probably simplify. 3 minus 1 will be 2 minus 2y minus 2x squared dy dx. Sorry. Now we're ready to integrate. Oh, this might not go well. Integrating y, 2y minus y squared minus 2x squared y from 0 to 1 minus x squared dx. Oh boy. Well, at least evaluating, these are all y values, at least evaluating them at 0 will all be 0 here. So we can ignore the second one. So it's 2, let me do bracket here, 2 times 1 minus x squared minus 1 minus x squared squared minus 2x squared times 1 minus x squared dx. Can we just skip the algebra and the calc 1 here? You can all do that. That's the kind of thing you look at and you're like, oh, I know how to do that. And you kind of roll your eyes because like, oh, this is going to be tedious. But you know how to do it. You can do it. Any questions on the setup for number 16 here? It's a good volume question. Thank you, Daniel. Any questions about this one? So hard. I'm so used to making eye contact with everyone and looking at everyone in the class. But in order to look at everyone from the class, I have to look at the camera and then I can't see anything. All right. Any other requests? We got time for a couple more here. Right. Lisette is asking about number 21. 21? Yeah, 21. Ooh. Ooh. Evaluate the following in cylindrical coordinates. I will tell you how I like to do these. Because it says cylindrical and it's like this dx, dz, dy, I struggle with like, what am I even integrating over? What is the region? I don't even know what the region is. So I like to I don't like to do a conversion, just jump in and do a conversion. What I would do instead is let me figure out what this region is. So x is going from 0 to square root of 1 minus y squared. Z is going from -2 to 2, and y is going from -1 to 1. Well, in the xy plane, this means x goes from 0, ooh, this is going to be sideways, semicircle sideways. X equals square root of 1 minus y squared. Okay, and then z is going from -2 to 2, so kind of like into the document and coming out of the document will be -2 to 2. So if we're going to draw this x, y, z, that you got to be careful. That graph is actually behind us here. Do you see it? X equals, no, it's above, it's positive x. Positive x. I don't know what I was thinking there. Positive x. That's x equals square root of 1 minus y squared. But then we're going to go down to and up to. I feel like I can't label that. Maybe over here. Down to and up to. So I'm going to go up to, kind of draw an invisible axis that's parallel. Kind of try to draw a parallel semicircle, and then down to, same thing. I'm going to draw an axis that's parallel, and then try to draw another kind of semicircle down there. So I don't know if you can see, it's basically half of a cylinder. I don't know if you can see that, half of a cylinder. X goes from 0, that's the YZ plane, out to the semicircle, square root of 1 minus a y squared. Z goes from below the xy plane, -2, to above the xy plane, +2. And then y goes from -1 to 1, so we do have the whole thing, -1 to 1. If it went from 0 to 1, it would just be a quarter of this cylinder then. So for me, I need to do that first. Then I will do the conversion, and then I'm basically going to redo the whole thing and just do the triple integral over the region of 1 over 1 plus r squared squared, and then dz r dr d theta. Changing my dA from some combination of dz dy dx, they're in a different order this time, but it doesn't matter, and convert it to, or sorry, not dA, dv, convert my dv from rectangular coordinates to cylindrical coordinates. And then finally, lastly, I will do the bounds. This is my recommendation, my personal recommendation. And now I'm going to ignore the original bounds, totally ignore the original bounds, and look at my drawing, look at my region. By the way, you'll notice the 1 plus x squared plus y squared became 1 plus r squared, and you think, how the heck am I going to integrate 1 plus r squared squared? Well, you have an r in the numerator now. dz, dr, d theta. You have an r. You have an r from the dv. Okay, well, z we already know. Z goes from -2 to 2. What about r?
0 to 1.
0 to 1. And then what about theta? You might, it's kind of hidden here now, but you might look at the xy plane for that. Theta is the angle from the positive x-axis.
Pi halves to 3 pi halves.
Good thought. That would give you the other half. It actually would give you the same answer because there's symmetry. But pi halves to 3 pi halves would be sweeping out this other half. And again, it would give you the same answer here. So it's actually okay, but it's incorrect. So you would want to go from negative pi over 2 to pi over 2, or you could, if you wanted to do double from 0 to pi over 2 because of the symmetry. You could in fact, you could double the z symmetry also. Because the same area volume below and above. Or you could say, screw you, man, this is half a cylinder. I'm just gonna go 1/2 pi r squared h, which would be 1/2 pi r is 1, h is 4. There you go, 2 pi, done. Oh, no, you can't. No, you can't. Sorry, I'm getting ahead of myself. Oh, no, I got ahead of myself. There's a function. We have to integrate the function. Ah, shoot. No, we have to integrate the function. We're not integrating one. We're not finding the volume. So you do have to do the integral. You do have to do it. I really think that the process that I'm using here is what you should take from this. When you're integrating a function over a 3-dimensional region, I really if you have the integral. Now, if you don't have the integral and you're just describing the region, just draw the region or imagine the region, kind of think about what coordinate system would work best and develop it from scratch. If you're given the integral, you do not need to use the coordinate system you're given. In this case, of course, they told us to do it in cylindrical. And my recommendation would be to draw the region first, or picture the region, maybe use some graphing tools if that would be helpful. Graph that region first and figure out what the region is. And then you'll notice the step that I have here above. I converted the function and I converted dv, but I did not stress about the bounds yet. I did not refer to the original bounds to get the new bounds. I got the new bounds from the region. The region is what you should be using to get the bounds. It's almost impossible to convert old bounds and use the bounds themselves to convert to new bounds. It's like practically impossible to do that. All right, that was a really good question, Lisette. I hope that was helpful to do. We're not going to finish this one. It's pretty easy to do. You do a U substitution, and then actually you don't do that initially because you're doing dz first, but the z and the r and the theta are all just integer, or not integer, just real number bounds. So the integral is as simple as it gets. Okay, I think that is it. I can stick around if you have some additional questions. I'm going to stop the recording now and end class. The exam is currently posted. And again, my request is that you please feel free to continue studying. You can take until tomorrow night if you want to. Keep studying, doing more examples. You could watch this video again. You could watch the other videos. Totally fine, no problem at all. But that you finish your studying and have your formula sheet ready to go, and you're all set. Okay, now I'm ready. I'm going to sit and do my exam. So that's my request, to please do that. Okay, that is it. I'm going to stop the recording, but I'm